Okay, good morning everyone. Sorry about the technical difficulties. Okay, so we were talking about vectors last lecture, so let's just recap that a little bit. So this chapter is really not so much talking about the physics of vectors, it's just more of a mathematics kind of presentation of the properties of vectors and things like that. And the point of this is that we'll be talking about motion in 2 and 3 dimensions later. So this means that we'll need some vectors, and so it's just establishing the formalism for that. So as you probably all know, vectors are quantities that have some magnitude and direction. And we looked at various examples of vectors versus scalars. Maybe our first example of vector is displacement vector. So it is the change in position from the initial to the final point. So we know in one dimension it's the final position minus the initial position. In the vector language it's exactly the same, except that everything is done with vectors. It's a path-independent quantity. When you do vector addition, it is basically the rule is that if you're doing graphically, you're doing it from head to tail. So you write one vector, and then if you want to add another vector to it, then you put the tail of the second vector at the position of the first vector, like in this diagram, or up there. So in terms of, say, displacements, if you had two separate paths and you wanted to work out where you end up after 2 displacements, say A and B, then you just add those vectorially. And so the total displacement of 2 displacements would be A plus B, where A and B are vectors. It works out that S is itself a displacement too, because if we look at the definitions of A and B, where say we've got point B, point A, that is a displacement vector between these 2 points, and then the displacement vector between these 2 points is little b, then when you add them, then these b's cancel, right? So you just get the displacement of the final point minus the initial point. It doesn't really matter actually that you pass through B. In terms of S, all it cares about is where you ended up, where you started with, and the intermediate point actually doesn't really affect it. And components of vectors, this is essentially kind of like writing the coordinates of the vector down, which is probably how you first encounter vectors. So if you have a vector, then we can work out what its, say, x and y components are by just forming a triangle here. We've got a vector that's in some angle, pointing some angle, some length, and you project basically this vector on either the x or y axes, and we know that the length of this component here will be just given by just trigonometry. So a cosine theta is this horizontal component, and a sine theta is the vertical component. And we can likewise go the other way and work out what the length of the vector is just by Pythagoras' rule. So say you had only the x and y components, and we can work out the length by Pythagoras. Or we can work out the angle just by, again, trigonometry. The opposite side over adjacent is the tan of the angle. Okay. Maybe I didn't really go into what I meant by this sentence. We'll go into this a little bit later, but the reason why, mathematically you kind of view the vector as more the fundamental object, and then the coordinates as being a kind of a secondary object, is because basically the coordinates are, it's like your reference system. You can choose your coordinates as you like, and it's like your viewpoint of the vector, which of course if you look at it from different angles, or say this coordinate was like rotated like 45 degrees or some other angle, obviously these components would be different. And so even though when you first probably learn about vectors in high school, maybe even before, you sort of, at least I was introduced to it as kind of the coordinates, right? Like you sort of view it as the coordinates are the main thing, but in fact it's not really that the coordinates are the main thing. You know, you view the vector as an intrinsic object, and the coordinates are kind of arbitrary according to how you view it, but the vector itself never really changes, right? So the vector has an intrinsic kind of truth to it, but the coordinates just depend upon how you view it. So we'll come back to that point later. Okay, so let's just do this question. So in this set of figures, which of the indicated methods for combining the x and y components of the vector A are proper to determine that vector? So basically what we want to do is just look at each of these figures. So I made it a multiple choice, but how about we just go through each one and we just collectively say whether it's correct or incorrect. So so this in this figure is this resolution of the vector correct? No, right, yeah, some of you shaking your head. So it's not right, because the vector's pointing this way, yet this one is pointing sort of the other way, right? So at least the components should be somewhat facing the same direction. Like if it's pointing the completely opposite direction, obviously it can't be right. What about this one? No. Okay. What's wrong with this one? Yeah. Which one? So is AX this component? Does that look right? Yeah, the Y one looks wrong, right? So AX, I think this one is okay, because it's, you got the vector here, and this is the projection of the component that way. But this AY is pointing the wrong way again, right? So it's pointing the wrong direction again. How about this one? Yeah, this one looks right, because that's the same direction, not the same direction. What about this one? Correct? Oh yes, right. Okay, yes. Yes, okay. Yeah, I think this one is also right, because this one plus this one gets you at the final position. This TV is very glitchy. I asked IT to try and fix up this problem, so hopefully we'll have it better by next lesson. Okay, what about this one? Incorrect, right. And what about this one? Yeah, correct. So in terms of my multiple choice, I think the D, all of the above, as in C, D, and F. Okay, so we're going to look at some general properties of vectors. So this is, again, it's more of a mathematical kind of view of what vectors are. You define vectors and you examine what are their general properties that are true for all vectors. So the first one is this so-called commutative law. So that basically means that you can add vectors in any order that you like. So you can add, when you add vectors, as I said, you do a head-to-tail addition, right? Now, of course, we can choose the A and then add B to it, or we can start with B and then add A to it. We can conceivably do both. Does it matter? And the basic answer is no, it doesn't matter. As you can sort of see from this diagram, you will always get the same answer regardless of which vector you start with. So this is a kind of a graphical view of it. Of course, I could, get some angles and kind of prove it, but probably I think for most of you, it's you've seen this before, so I don't think I will go through it, and it looks pretty plausible just from the diagram, right? Now, another way to prove it would be to prove it by components. So for example, if we choose some axes and then resolve the vectors into their x and y components, ax and ay, bx, by. Now, we know how to add vectors. Well, okay. I guess I didn't really tell you, but I mean, I guess I'm telling you now that when you add vectors, you can add them by components. So a way to add two vectors, you can add it by head to tail, or you can simply add the components of the vectors, and I guess maybe you guys don't really need convincing, but so if you've got two vectors like this, then the reason why we can add the components and it will give the resulting vector is, I guess you can see it from this graph, that the x component of this is here, and then the x component of b is here. So, of course, when you add them, the x component of the whole vector is just ax plus bx, right? Because you just add this part and this part together. And likewise with ay and by, so the y coordinate of the resulting vector here is just the sum of the y components. So when you are adding the vectors in the reverse direction, then of course, because a plus b is the same as b plus a, you can also see that the commutative property is, you can prove the commutative property from there. Okay, another vector property is a little bit similar, but if we consider three vectors, then it's a so-called associative law. This basically means that you can you can add the vectors in any order, and it doesn't really matter what the final result is. So for example, if you've got three vectors a, b, and c, then you can first start by adding a plus b, and then find that, then add that result to c. Or you could start by adding b and c, find that, and then add the result to a, and you will again always get the same answer. So graphically, it would look like this. So for example, here's my vector A, here's my vector B, here's my vector C, right? So the three vectors that we're trying to add here are these two. So if you start by adding, say, B plus C, okay, so these two together, then basically the resulting vector there is this vertical line. And then if you add A to B plus C, so that's the left-hand side of this, then you get something that's looking like that. But if you add, say, A plus B first, so that's adding these two vectors together, then and the resulting vector is this sort of faint green one. And then you add the faint green one to C, and then again you have something that looks very much like the other one. Okay, so you can probably, again, prove this graphically. Again, you could also prove it by components, and I think maybe by components it's even easier to sort of see because it's just an extension of the argument here. So because so our resulting vector here is going to be the black one there. Now the final vector is of course going to be have a vector with components of ax plus bx plus cx, and then ay plus by plus cy. And because you can add numbers in any order that you like, obviously you can add the vectors themselves in any order you like, and you will get the same answer. So it's a similar type of argument to show this associative law. Okay, and subtracting vectors. Actually, we kind of started off already. We already started using this before we even said what it was. So remember when I said the displacement is the difference between the final vector and the initial vector. So what is the difference? How do you take the difference of two vectors? Well, you simply add the negative of the vector that you were talking about. So, for example, if you wanted to do something like a minus b, okay, I'm going to use the other screen. A minus b, so that means actually you do a, and then you add the negative of b. And what is the negative of b? Well, that basically is just the same vector, but it's pointing the opposite direction. So if b is this thing that's pointing sort of diagonally down to the right here, then negative b is the vector that's pointing diagonally up to the left. So you add basically a and the negative of b, and so the addition diagram would look like this: a, and then you add the negative of b, so that way. So this thing is the difference between a minus b. Okay, and of course, but in terms of components, the negative of the vector is if you've got a vector ax and bx, then the negative of the vector just in terms of components would be minus ax. Sorry. Ax, ay. The components are all the negative too. Okay. All right. So let's try this one. Magnitudes of the displacements of a and b are 3 and 4 meters respectively. Okay. And then c is a plus b. So the sum of those two vectors. Considering various orientations of A and B, what are A, maximum possible magnitude for C, and the minimum possible magnitude? Okay, so let's do A first. So what would be the maximum possible magnitude of C, which is the sum of those two vectors? Right, 7, yes. So probably, I think everybody gets it, but just to draw a picture of this, so basically what this question is getting at is that, well, okay, so A is 3 meters, B is 4 meters, but we're not told like what angle it's pointing, right? So in principle, so A could be like this, so this is 3 meters, and then, B like this could be 4 meters, right? And so we're not told what this angle is, nor say this angle here. So the question is like, we've got this angular degree of freedom, so that's why we can't really say what is A plus B, but we do know that depending on these angles, it will be well, within some range, right? So you couldn't possibly, for example, add A and B and get a vector that's like 100 meters long, right? It's just impossible because it's, these two vectors are not long enough. So the maximum possible distance is 7 because that's, when these two vectors are in complete alignment, then the total vector will be length 7. But of course, we still don't know what direction that whole thing is pointing. All we know is that these two vectors are in alignment, but it could be pointing all this way, or it could be pointing all that way, it could be pointing any way, but we still don't know what it is, but we know that at least the maximum length will be 7. What about the minimum possible magnitude? One, right. 1, presumably you did 4 minus 3, which is correct. So I've got, in question D, I've got a minus 1. Why not minus 1? Right, yeah, it's just wording of the question. So magnitude means actually just the length of the vector, which is always a positive quantity. So it's sort of a trick question, if you like, or a trick answer. Okay. Right. Next is unit vectors. I first encountered this in first year physics myself, and I always thought, what's with these unit vectors? Why do we have these unit vectors? Has anybody seen unit vectors before? Okay, some of you, yeah. So I remember being confused by this in first year physics because it looks awful lot like just components. We've already talked about components. A is, components AX, AY. And, okay, so firstly let me just explain what it is. So another way to write down what these vectors are is in the following form. So, for example, let's say that we've got this vector A, and in component form it's AX, comma AY. So that's, we set up some axes and we define it like that. B, likewise. Now, let's define these things called unit vectors. So let's consider the unit vectors, which are just also special vectors. They're just a special case of vector where the vector happens to point along the coordinate axes. So I, this vector I, is the vector which is pointing along the x-axis, and it has a length of 1. It's just a special, example of vector. Vectors, in general could be, any length, any direction. But we're just going to single out a couple of these vectors, and then we're going to call them unit vectors. Obviously, they're called unit vectors because they have length 1. Right? J is the vector that's pointing along the y-axis, like this. Again, it has a length of 1. In the coordinate form, it is 1, 0. J is 0, 1. I is 1, 0. And for some reason I didn't write down K, but in 3 dimensions, we're working in 3D, then K, okay, let me write down that's the 2D version. 3D version would be just this, I, J, K, and again it's the vector that's pointing along the z-axis, and it is length 1, okay? Okay, so now we've defined these unit vectors. And then we can rewrite our vector A in the following form. So we know that the A vector has some component AX, AY. Okay, so let's use our x-axis, use our y-axis. What we just defined were these unit vectors. Maybe I use a different color. Here's our unit vector I, here's our unit vector j. And then we have some arbitrary vector A, and it has the components, coordinates, if you like, AX and AY. Okay, and we can rewrite this A vector in terms of these unit vectors, and we can do that because, for example, we can make the vector that has length AX pointing just along the x-axis. So let's think about what this, so maybe I'll use yet another color. So we can think about what that vector is. Well, it's because this is unit length, it's got length 1, and this vector that we're trying to rewrite has a length of AX along this direction. This vector here would be AX, which is just a number, multiplied by I unit vector. Yeah. Likewise, this vector here, what would this vector be? So the direction of this vector is j, yeah? And then to make it the right length, yeah, AY times this j unit vector. Okay, and then this vector here is, as we said, you know, we can add two vectors. This thing is just one vector, this is another vector. So we can simply rewrite this as something like that. Now, if you just look at this, it's pretty much, it's kind of obvious that if this point has coordinates AX, AY, it's always like this, right? So, you know, whatever your coordinates are, just put an I here and a J here for this one, then add them, right? So I always, you know, so let me go back to my story of me in first year physics. So I thought, well, this looks really redundant because we just learned it like this way, right? This just almost looks like writing it like another way, right? Because it's always the same. Like you write it as AX, AY, you know, in the brackets, or you just multiply by the unit vectors and you add them. You know, what's the difference? Like what's the use of this thing? And indeed, like in this form, it's not particularly useful. But what we're going to do is the cross product, and for the cross product, it actually is, I would say, useful for working out what the cross product is. So we're going to get onto that in a minute, but for now, I think you can just purely view this as sort of just a kind of a slightly different way of writing the usual coordinate thing, right? So if we got AX, AY, then just consider this as just another way of saying the same thing, but nothing really dramatically new really there. Okay. So, for example, if you want to add two vectors in this unit vector notation, the way that you do it is something like this. So say you got two vectors, So the original component coordinates were, say, ax, ay, so we use the unit vector way to rewrite it slightly differently. And then when you add them, then you do something a little bit like you might be used to in algebra, where you can just group various components, various terms together. So we just view these things as some kind of algebraic objects. So we've got 4 terms here, and then you say, okay, well, here's an I, here's another I. We can factorize that. We can write it like this, right? For the J unit vector terms, we've got AY, BY, and then we can rewrite it like that. And for those of you who are used to just adding vectors with coordinates, this is perfectly, obvious, because when you know that when you're adding 2 vectors like this, then in terms of the coordinates, of course we know that it's ax, bx plus ay plus by. So, basically the same. Okay. But as I said, we'll get onto a case where it's actually useful. So far it's not very useful, but it will be useful maybe later. Okay. In the figure here, what are the signs of the x components of d1 plus d2?
Positive.
Yes, positive. Both of d1 and d2, their x components are positive, so you're going to be adding two positive numbers together, which is always positive. Even easier, just look at the graph. Obviously, it's positive, right, in the x direction. What are the signs of the y components of d1 and d2? I think I saw some of you mouth positive, which is correct. So again, it's just this is the resulting vector here. It's positive. What are the signs of the x and y components of d1 plus d2? I don't even understand the question. Signs of the x. Sign and y sign. Oh, right, sorry. Okay, so sorry, I jumped ahead. I thought this was d1 plus d2. I think what we were supposed to say in A was d1 has a positive component, d2 has also a positive component. D1, y component, this is positive, and I think d2 is negative, yes? Okay, so actually it's a 2-part question for A and B. And then C is basically what I immediately jumped in and answered, which is the sum of both of these two, which are positive. I think the question is so simple I confused myself. Okay. All right. Okay, so now let's get back onto the point that I was talking about before with how we kind of view these vectors as being sort of intrinsic objects, right? So, as I was saying, often when you first encounter vectors, you almost think of them the same as just, the coordinates, right? Sort of ax, ab, it's kind of the vector. But the point is that these numbers are somewhat arbitrary, because I could have chosen my axes to represent this vector in a different way, right? So what if I had my axes, it's going to get messy, but if I had different axes like this, you know, if that was x, this was y, sorry, x prime and y prime. Now, in my new coordinate system or new viewpoint of this vector, obviously this would have different coordinates because I've rotated my coordinate system. I'm not going to get the same numbers. And from a physics point of view, this has a lot of relevance because, well, this comes up a lot in anything that you pretty much do. But you know, if you're an experimentalist who's trying to observe some phenomenon, you know, but you always have some viewpoint, right? You're always looking at some object from some direction. And so the way that I see some object is different from the way that some of you will be seeing it, simply because of the angle that we're looking at it is different, right? But I think we all agree that we're looking at the same object, and then the object has some element of, well, reality, right? So it's not that somehow everybody's got their own different idea in their head and it's you know, disconnected from each other. We tend to all agree that somehow things are real and we all look at them and it's really there, right? So vectors are really sort of this kind of idea, and you know, this is some kind of meme where you you know, you have some object, and it's kind of a, you know, extreme example, if you like, where the same object can look entirely different according to just how you view it. So this person would think that it's square, and this person would think it's circular, but in fact it's, you know, some cylindrical shape like this. So so that's why we kind of view the vectors as being the real object, and then the coordinates as being somewhat arbitrary. And of course, when we rotate our coordinates, we don't change anything about the vector. It remains exactly the same. It's pointing in exactly the same direction. So its length is the same, but how you represent it in terms of coordinates might change. Okay, so yeah, okay. Well, okay, so maybe one thing that you might, to sort of convince yourself of this, is looking at things like the length of the vector. So just to show you that the length of the vector is going to be unchanged. For example, you know, consider you have some vector here, and say originally it has some angle theta, and so say the original length of this would be a little a, and then the components of this would be a cosine theta and a sine theta. But we could set up a different coordinate system. Say this is x prime and this is y prime. It's gonna, hope this is not going to be too messy. Well, okay, yeah, well, all right, maybe we'll do an example like this. So then, in this case, the coordinates of this one will be a different angle, which we can call phi. The length of this side will be a cosine of phi, and then the length of this side will be a sine phi. But we of course know from Pythagoras' rule that if we want to find the length of this object, then So in the red coordinates, the length of the vector A will be square root of A sine A squared sine theta plus A squared cosine squared phi. And this is just the magnitude of A. And in the blue coordinates, this same quantity would, of course, be this. And you get the same answer regardless of the fact that, these angles are totally different. So regardless of, what angle that you choose, certain properties of the vector will remain invariant, right? So if we chose some other quantity that was not kind of intrinsic to the vector, like things like the components of the vector are not really intrinsic to the vector, but the length of the vector is something that's intrinsic to it. So this is why it doesn't matter what coordinate system you choose. If you are looking at some property like the length of the vector, it's the same. Okay. All right. And the final topic that we're going to do is to talk about how you multiply vectors. So we've been talking more about how you add vectors or you subtract vectors, things like that. But you can also multiply vectors, and we've actually already kind of done this implicitly here. But first type of multiplication, and so there's different types of multiplication when you are talking about vectors. So the easiest type is the one that we've already encountered, which is when you multiply a vector by some scalar. So just scalar is just a number. So if you multiply a vector by some number s, then you'll get basically the same vector, but it's pointing, it's pointing in the same direction, but the length is going to be either longer or shorter, right? Unless the factor of s is 1. So working this out in terms of components is easy. You just simply multiply the vector by the components. So the new components are just s times ax and s times ay. Or in this unit vector notation, same kind of thing. You multiply s by the vector, you multiply it out. And again, you have these new components. Well, in this case, it's the coefficients of the unit vectors, sax and say. All right. But you can also multiply two vectors together. So how do you multiply a vector by a vector? Well, so you can come up in principle with all kinds of crazy rules for multiplying two vectors together, and in a way you can define it like more or less as you like, but a lot of these definitions will not really be particularly useful, right? So there's only a couple of types of definitions of multiplying vectors where it has some interesting properties and some physically relevant properties. So what I sort of mean is that, in principle you could, invent any kind of formula for of multiplying two vectors, because all this really means is that you take one vector, or take two vectors as inputs, and then it will output something. And how we define what is happening in this box is, well, you can define any kind of operation that you like, but a lot of them will not really have any kind of physical relevance, and it will also not really obey some nice mathematical properties. So we're going to look at two particular potential definitions of multiplication which is the scalar product and the vector product. So for the scalar product, what happens is that you take two vectors and then you do some operation on it, which I'm going to define just down below here. And then what it will eventually do is output a number. Okay, and what happens inside this blue box is is basically defined by basically this particular formula. And you might ask, so why this particular formula? Well, it goes back to saying that, well, it has some nice mathematical properties and it ends up being useful also in physics. And so basically the rule here is that, okay, so you got your two vectors, and then you multiply the x components together, you multiply the y components together, multiply the z components together, add them, and that's your output of this function. So why is this a nice what nice mathematical properties does this have? So it goes a little bit. I'm not really going to explain it so much, but it's very similar to this kind of idea. So remember when I calculated the length of the vector, it didn't really matter what coordinate system I chose. I got the same answer, right? And for this scalar product, it so happens that I could choose any coordinate system for vectors A and B, and I will end up getting the same answer. And so that's kind of the magic aspect of this formula, that it's invariant under your choice of basis. And that's quite a neat property because it sort of suggests that it is something intrinsic to those two vectors themselves, right? Like, I could invent some weird formula where, I take two vectors like this, and let's say I just defined it as, 3ax by plus 5, there's nothing stopping me from defining something like that. But the problem with that is that that's going to give me different answers depending on like what basis, what coordinate choice that I actually choose, right? So if I choose a different coordinate system, I'm going to get a totally different answer for ax and by, and that would mean that if I define something like that, then nobody would agree on what this thing here is, right? So if I measured it and calculated this thing for the two vectors, then I'd get the answer 3, and then you did it, you get 5, and then somebody else does it, you get 10, and so just like it's not very useful. But the thing about this formula is that if I calculate it, with my coordinate system, calculate it, I'll get 5, and you'll get 5, and you'll get 5, and everybody will get 5, right? And then so somehow that that's quite a nice property because it seems to suggest that that's something. It's not got to do with how you measured it, but how something got to do with the vectors themselves. It's kind of intrinsic property of them. So that's kind of why this scalar product is so useful. And well, first mathematicians identified that they went, oh, that's quite a nice property, and then physicists could sort of apply it to different systems and also find that it's very useful. Okay, so that's scalar product, and this might be how you have maybe seen it before, for those of you who have seen scalar product before. But I would say that this is not really the definition. It's more like that this is a property that follows from the definition. So I would say I'll call this the actual definition, right? That's kind of the main rule of how you calculate the scalar product. And this is just a sort of a neat way of calculating it. And how does this arise? So let's just go through it. so we want to calculate the dot product of two vectors like this, and we're going to try and show this formula. And firstly, so we better understand what are these definitions in the formula. So A is, of course, the length of the vector A. B is length of vector B. Cosine of phi, so this angle phi means actually this angle that is between the two vectors, right? So, maybe we can, I might just start the coordinates down here. So phi is this angle that's between these two guys. Now, okay, the sort of definition way of calculating a scalar product of B would be to simply look at these components. So here we've got Bx, here we've got By, here we've got Ax, Ay, and so again it would be just Ax, Bx. So you add the two, you multiply the two x components, you multiply the two y components, and that would be it. But using this property that this dot product is actually invariant under these rotations, we can choose a coordinate system that just makes actually this quantity like quite simple. And the idea is, so let's choose a coordinate system that is just like this. So let's choose our coordinate system x so that it's running right along B, right? Let's choose, well, we have the other coordinate system, other axis you have to choose so that's perpendicular to it. So we can't do anything about it. We can't choose it really along there. Okay, now in the dashed basis, so x dash, y dash, what's the coordinates in the x dash, y dash system? What's the coordinates of this B vector? Sorry?
Just a
right, but I'm wanting to hear like a 2-point coordinate system. So
it's B0.
Yes, B0, exactly. So this coordinate is B0. This is in the dashed system, yes? Okay, and then this A vector, we know that the angle between them is phi, right? So what in the dashed coordinate system, so we have to kind of draw maybe a bit of triangle here. What's the coordinates of A? You've got to sort of tilt your head a bit. Sorry, with
0 A sine.
0, x 0.
0.
X coordinate 0. No, x coordinate would not be 0 actually, but I think you said a sine phi, right? So I think that
X will be
a cosine, yes.
and Y will be A sine.
Yes. So a cosine phi, a sine phi, because this angle here is phi with respect to the red coordinates, yes? And then this A has length of A. And so just looking at this triangle and then, looking at, this is the right angle. This is a cosine phi. This is a sine phi. Okay, so now we're going to use, instead of the ax, bx, ay, by, we're going to use the coordinates in the dashed axes instead of the original axes. Yeah. So if we do that, then it's the same rule. You look at the x components and you multiply them together. So sorry, no brackets. So it's this one, a cosine phi times b. And then the y ones, what happens to the y ones? It's ay, by, right? So the rule is that you multiply the x's together, and then you add that to the product of the y's together. So what's this one going to be? Sorry, the
A, B.
yeah, but I just want to do it like component by component. So the x component was this, right? And then what's the y component? 0, right? This is the trick, right? The fact that this term is 0, you don't even have to think about it. So you've only got the x component. So it's AB cosine phi. So it's a special, special way of writing it, and by choosing the coordinates, it is a special case where the formula simplifies a lot. So, so that's why basically the scalar product can be written as AB cosine phi. Often you sort of just learn that and then you kind of take it for granted that that's what that means. But actually it's sort of the wrong way around. It's, the original definition has really got to do with the multiplying the components and adding them, and then this is a special case. Yeah. Sorry. Yeah.
Can the B vector, the S component of the B vector, be B cosine phi? And that's it.
B cosine. Oh, you mean like choosing the axes in a different way so that the x component is B cosine phi?
I mean, in the dash axis.
Yes.
Can be also to use the angle phi in the representation of coordinates.
Yeah. So I think what you might be getting at is that, so if you choose the red coordinates, right, then in the red coordinate system, this thing is always B0, and there's no cosine phi because we chose the coordinates right along there, so there is no phi in terms of representing B. The only phi that appears is to represent A, and it's specifically because we chose this red coordinate so that B lies exactly along. Sorry, the x dash axis lies exactly along B, right? But maybe what you're getting at is that I could have also chosen something like this. I could have chosen is B, is A. I could have also chosen like x dash dash to be like this, and then there'd be y dash dash. In the blue coordinate system, now this time A, we chose x to be lying exactly along A, right? So in this coordinate system, this vector would look like A0, right? And then this time, we have to draw a triangle like this. B is going to look like B cosine phi minus B sine phi, right? So in the blue coordinate system, now B has the phi because we chose the coordinate system that's lying along A, right? And then we can do the same thing we do our rule, multiply these guys, so it's AB cosine phi, and then add that to 0 times minus B sine phi, and the second one just drops out again, and again it's AB cosine phi. So we can do it in a different way, and we'll still get the same answer. And the reason why phi didn't appear here is just because of the special way that we chose axes. So, does this answer your question? Okay. Alrighty. Okay. So let's do this one. Vectors C and D have magnitudes of 3 and 4 units. What is the angle between the directions of C and D if C dot D is equal to part A 0? So what would be the angle between them if it's 0? Right, 90 degrees, because this thing, so this is where using this formula is useful. If this thing is 0, cosine must have been like 90 degrees. What if it's 12 units? Right, yeah, 0. Yes. And what if it's minus 12 units? 180, yeah, because cosine of 0 is 1, so then 3 times 4 will be 12. Cosine of 180 is minus 1, so then it'll be minus 12. Okay. All right, and then finally we get onto this vector product, or cross product sometimes it's called. And again, this has sort of the fundamental definition, which is actually not really 3.24. I would say that the real definition of the cross product, vector product, is actually this thing down here. And so, you know, this looks like a horrible formula. So what's the rule? Okay, so let's look at it. So it's defined like this. Oh yes, and this thing, you need to work in 3 dimensions for this one. Okay, so we've got 2 vectors, AX, BX, sorry, AY, AZ, BX, BY, BZ, okay? And we're going to multiply these 2 vectors according to the vector product. And there's this really weird thing that you do. So to get the x component of this resulting thing, you look at all the components which are not x. So that's these ones here. So you look at AY, BZ, and then AX, BY. And then you multiply the y and the z together. So you multiply it sort of, you know, like diagonally, like this, and then you subtract them. Okay, it seems super weird rule. AY, BZ minus AZ, BY. Okay. To get the y component, you look at all the components which are not y, and then you multiply the ones like kind of diagonally like this. And then for this one, with this one first, so it's AZBX. Sorry, AZBX minus AXBC. For the Z component, you look at the components which are not Z, not Z, and then you multiply it and then subtract it according to ax by minus ay bx. Okay, so that's the rule. Have you guys seen this before? Yeah, maybe most of you not. Okay, so as a rule, I think many of you would think that's crazy. That's a crazy rule, right? Like, the scalar product, okay, fine. You multiply these things, add them together, multiply again. That seems kind of systematic, right? But this is a pretty bizarre rule, right? You look at the components that are not, and then you multiply, and then you subtract them. What in the world is going on there? And you would not expect this, if you just didn't know anything, you would not expect that this would have any kind of nice mathematical properties, right? You would think that this rule is one of those, a crazy rule like my made-up function rule that would not satisfy any kind of nice properties. We'd all get different answers. But it's not true. This actually, miraculously, does actually have this kind of basis invariant rules. So, pretty strange, but it works. Well, I haven't really proven it to you, but I'm just saying that it does. So that's the fundamental rule of how you do the cross product. Now, I can hardly remember this rule, so I have to sort of peek at the answer sometimes to make sure that I'm getting it right. So here's where the unit vectors are actually kind of useful. In my opinion, this is why we use unit vectors in the first place. Okay, so that you can try and remember the rule as I sort of described it, but even I don't really have confidence that I'll get it completely right. Particularly where you might mess things up is to have the wrong sign here, right? So you might accidentally have ax bz minus az bx here, for example. So here's another way to work out the same thing, but we're going to use the unit vectors. And the idea of using the unit vectors is to first work out what is the rule for the cross product for the unit vectors, right? Okay, so maybe we can just do an example here. So for the particular case of the unit vectors, so I is 1, 0, 0, right? And j is 0, 1, 0, right? So let's try and work out, according to, that was the definition of the rule, right? So let's work out what I cross j is. Okay, so let's look at well, we can just look at this formula here. So if we apply this formula, this is aybz minus azby. What's the x component going to be? Okay, let me walk you through it then. So the rule is something like, okay, so the x, to work out the x component, we cover up the x's, and then we diagonally multiply these ones and then subtract them from each other, right? So 0 times 0, 0. 0 times 1, 0. So 0 minus 0, 0. Okay. Y component, okay, we diagonally multiply these things, so it's got to get the right order this time. So it's actually this one first. 0 times 0 minus 1 times 0. It's 0. Okay.
Sorry, why is not ax bz minus az bx?
Sorry, y is.
I just made the second part because he just followed the.
Sorry, the.
I mean, like for the first part and the third part, we always start from the like the. Yeah.
So here, why isn't it ax
Yeah.
bz minus az bx?
Because for the first and third part, we always follow from the left to
Yeah.
the right and minus the left, right to the left. Why is just the second part change?
Well, you might. Okay, so probably the real answer is its definition.
Okay.
I mean, that's the definition. I mean, it's already crazy. You know, why ask why? Because it's crazy. You know, there's no rationale to this. It's how bizarre. You know, what is this? Covering up, crossing multiple. You know, I mean, it's crazy, right? But okay, but to give you a little bit more of a kind of a why, or at least a little bit of a rule, maybe you can think of it, the rule as being you cover it up and then you start from the one to the right of it, right?
Oh.
Yeah. And then so for this one, you cover it up, you start from the one to the right of it, and then if you sort of go around, and then you go this one times this one, because this one is sort of, if you think of it as cyclic, right? And then this one, okay, it's not, there's nothing here, but you go around here and then you do that, right? Okay, I mean, but that's still, it's not really an honest answer of why, because it's crazy. Okay, let's just finish this up, and then so here, what about this one? We cover up this one, 1 times 1. 1 times 1, come on guys. We're in university, 1 times 1. Minus 0 times 0 is 1, right? Yeah. Okay, so 0, 0, 0, 1. So this is unit vector k. We'll finish up there, but so that's like the first one, and well, we'll finish this up next week. But, yeah. Okay, so see you next week.